Great. So I'm really grateful for this opportunity to share my work looking at how permafrost thaw, glacier melt, and human activities like mining are impacting mercury exports across a wide variety of watershed types in the Yukon River Basin. And really, I'm going to be trying to tell a story about how my own understanding of what is driving high mercury yields from the Yukon River Basin has evolved over time. So I want to start off with a land acknowledgement to give my gratitude to the numerous First Nations on whose traditional territories this work has been conducted, and also to acknowledge that these peoples, many of their ancestors have lived on the lands across the Yukon River Basin for millennia, and many people there continue to practice traditional lifestyles and act as incredible stewards to these lands. And I'm very grateful for them for doing that, and also for their permission to conduct this work. So yeah, there has been an incredible amount of research over the past 2 decades or so that has really clearly demonstrated that rivers are one of the most important sources of mercury to the Arctic environment, where mercury is often elevated in food webs relative to the number of point source emissions to the Arctic. And so, because rivers are such excellent integrators of changes to the landscape, there's been an increasing research effort aimed to understand how fluxes of mercury to the Arctic Ocean from rivers, will respond to changes to the landscape due to climate change and human activities. And really, there's just 6 big rivers that drain more than half of waters into the Arctic Ocean. And I'm going to be focusing today on the Yukon River. That's this orange watershed here. And that's because the Yukon River is unique in a number of ways. One, it has a large glaciarized region in its southern headwaters. 2, most of it is in discontinuous permafrost. 3, a large portion of it was never glaciated during the last glacial maximum, previous glaciations. And 4, most of it is north of 60 degrees latitude. So it's been suggested that the Yukon River may show a response to climate change more rapidly than some of these other river systems with more southern headwater tributaries. And what really makes the Yukon River unique is that it has almost twice as high of an annual mercury yield than any of these other large Arctic rivers. And in that first estimate by Paul Schuster and team in 2011, they found that mercury concentrations at the Yukon River outlet correlated really strongly with organic carbon. And so they inferred that the main source of mercury to the Yukon River might be soils and vegetation across the Yukon River Basin. And with that, they suggested that as permafrost degrades due to climate warming across the Yukon River Basin, that mercury exports downstream may increase in the future. Not long after, Paul Schuster and team also published a study that took a series of permafrost cores across Alaska with increasing latitude. And they found that mercury concentrations in those cores increased with latitude, and that mercury correlated with soil organic carbon concentrations. And with that, they modeled the amount of mercury across the Pan-Arctic region. And they suggested that permafrost might be the single largest store of mercury in the entire Earth's surface system. And while the scientific community has been having a lot of back and forth on this model, and subsequent models by, for example, Lim and team in 2011 have suggested lower estimates for the amount of mercury in permafrost, I would still argue that the study had a really major cultural impact, with with articles in newspapers like the Canadian Broadcasting Corporation stating the world's largest deposit of mercury is in permafrost, and the Arctic is full of toxic mercury, and climate change is going to release it. So I'm sure you can imagine if you're someone living on the land, these studies may have introduced an element of concern in you. Not long after, Kira, who thank you for joining today, Kira St. Pierre and team published a study looking at mercury concentrations upstream and downstream of thaw slumps and the Peel River Basin. And they found some incredibly high mercury concentrations and methylmercury concentrations downstream of some of these incredibly large thaw slumps in headwater tributaries. Now, the Peel River is one of the northernmost tributaries to the Mackenzie River, one of those 6 largest Arctic rivers. And while St. Pierre and team did a really great job of carefully considering that the capacity for these small headwater tributaries to transport this predominantly particle-bound mercury downstream would be limited by the capacity of these rivers to carry these sediments out. They did also use Paul Schuster's model of the amount of mercury across the Panarctic region, and together with a model of landscapes susceptible to hill slope thermokarst, suggested that about 5% of mercury in the Arctic region might be released to downstream environments as permafrost thaws. So this study came out right around when I was beginning my graduate studies, and myself and my research team, we were really intrigued by this, and we wanted to look more closely at how various geomorphic factors could influence how various landscape types exported mercury downstream. So we conducted a study in the watershed right next door. We reached out to the Vuntut government and asked, could we do a similar study in the Old Crow River Basin? And you might be thinking, well, this is silly. Why did you go to the landscape right next door? Wouldn't you expect to see the exact same response? Well, what's different about the Peel River and the Old Crow River is the Peel River is right at the margin of the last glacial maximum. So ice sheets extended over this region, and there are really thick, ice-rich tills that the Peel River drains. In contrast, the Old Crow River drains a large glacial lake deposit. So the sedimentology there is different, and the relief is different. There are many thaw lakes and wetlands in the central portion of the basin, and there are many thaw slumps in the upland portions of the basin. And the Old Crow River also happens to be one of the northernmost tributaries to the Yukon River Basin. So in this landscape, we set out to collect mercury samples from tributaries either draining the flatland regions with thaw lakes and wetlands, or the upland regions with thaw slumps. We also collected samples of river water samples upstream and downstream of 4 of the largest thaw slumps in this river basin. And you can see an example of one of these thaw slumps debris tongues extending well into the Old Crow River main stem. And we also collected water quality samples at the mouth of the river to integrate water quality signals across a year. So what did we find? Well, mercury concentrations were incredibly low upstream and downstream of those 4 largest thaw slumps in the river basin. And we infer that this is because the materials being eroded actively by the river in a part of the year during July, it's more or less being diluted. This is because this river is a much bigger scale, and so we weren't able to observe an effect size. We also mapped the incidence and size of thaw slumps along the Old Crow River main stem, and we found no evidence to suggest that thaw slumps have been increasing in activity or size over the past few decades. So again, this is in complete contrast to the Peel River, where thaw slumps in this ice-rich till have been growing to really incredibly enormous sizes over the past few decades and increasing in activity. In terms of the tributaries draining the flatlands with thaw lakes and wetlands, we found really low mercury concentrations and also relatively low methyl mercury concentrations, less than 0.1 nanograms per liter. Still very low mercury concentrations in the upland tributaries and those samples from the above and below thaw slumps on the main stem. So again, contributions from thaw lakes and wetlands were diluted by the time they reached the Old Crow River main stem. So we inferred that while in glacially conditioned headwater systems where thaw slumps can enact a really major, really influence mercury chemistry downstream, in unglaciated landscapes at a slightly larger basin scale, at a larger river reach scale, although there were many thaw slumps across this river basin, really at every reach of the river that had a slope greater than 30 or 40 degrees, the thaw slump contributions and thaw lake contributions were diluted by the time they reached the river main stem. And finally, integrating over the course of the year, we found really low mercury concentrations and low methyl mercury concentrations, so less than 8 nanograms per liter, and less than 0.1 nanograms per liter methyl mercury. Concentrations were relatively higher during the spring flood, relatively lower during the period of ground thaw, although they did increase following rainfall and runoff, and inevitably some activation of otherwise inactive thaw slumps in the basin. But maybe more interestingly, we found that mercury concentrations correlated far more strongly with total suspended sediment, which was by and large inorganic in nature, rather than with organic carbon concentrations. So from this, we inferred that the main source of mercury in the Old Crow River might be simply crustal rocks, shales in the geologic units. And finally, and maybe most importantly, when we modeled the amount of mercury being exported out of this river system in a water year, we found a really low yield of mercury. And so this brought us back to this question of, well, if permafrost has been implicated as one of the main drivers of these high mercury concentrations at the Yukon River outlet, why was the mercury yield so low from the Old Crow River? And what else could be driving these higher mercury yields at the outlet? And right around this time, another major study came out by Kevin, as we were wrapping up that work, by Kevin Schaefer and team and Nature Communications. And they again used the model of mercury across the Panarctic region, published by Paul Schuster and team in 2018. They also assumed really minimal contributions from glacier melt or bedrock leaching, and they suggested that as permafrost degrades in the Yukon River basin, that mercury exports may double and then triple in the coming 2 centuries in a warmer climate. And they also suggested that methyl mercury concentrations in fish, the average fish tissue, may exceed EPA criteria by 2050. So this is less than a generation away. So again, I would argue that this study had a really major cultural impact for people living on the land in the Yukon River Basin, and it also had a big international reach with news articles like Reuters publishing mercury released by permafrost thaw puts Yukon River fish at risk. So this brought us back to this hypothesis. Was permafrost in the Yukon River Basin the source of high concentrations at the outlet? Perhaps we needed to study some of the landscapes that had been glaciated in the past and therefore had till sediments in them. Or was mercury that was used during the gold rush being reworked by modern day placer mining? Or is the fact that placer mining in the Yukon River Basin disturbs permafrost overburden perhaps accelerating mercury exports downstream? Or was there atmospheric pollution from across the Pacific Ocean stored in the glacial headwater, the ice in the Yukon River headwaters? Or were the glaciers in the southern headwaters simply scouring huge amounts of crustal sediment from subglacial and proglacial settings? And was that introducing high mercury concentrations downstream? And when we looked more closely at the seasonality of the data published by Scott Zolkos and team in 2020, we found that the Yukon River was unique in yet another way. Rather than exporting most of its mercury during the spring flood, it had its highest mercury exports during the summer. So we set out to sample widely across the central Canadian portion of the Yukon River Basin in the middle of summer in late July of 2021. And this is a region characterized by isolated, sporadic, discontinuous to almost continuous permafrost. There's several large placer mining districts. There are rivers that drain directly from glaciarized mountains and rivers that drain through these deep lakes with glacial melt sources. So specifically, we sampled one of the largest glacial rivers and intermediate-sized glacial rivers, 3 rivers draining deep lakes, and then a suite of rivers in sporadic through discontinuous permafrost with or without mining. And we also sampled the Yukon River at Dawson City, which combines all these rivers before these waters flow into Alaska. So what did we find? Well, the largest glacial river by far had the highest mercury concentrations at about 56 nanograms per liter. The second highest and third highest mercury concentrations we observed in the intermediate-sized glacial river and the Yukon River at Dawson City, which combines all these other rivers. In contrast, we found extremely low mercury concentrations downstream of the deep lake systems and the rivers spanning sporadic to discontinuous permafrost with or without mining in their catchments. And when we factored in the water yields of each of these rivers and their catchment area, we found that the White River, if you notice this axis break here, had 2 orders of magnitude higher mercury yields than the other river systems, with the intermediate-sized glacial river and the Yukon River at Dawson also having almost an order of magnitude higher mercury yields than the other rivers. For methylmercury concentrations, they were relatively higher in one of the glacial rivers, but below detection in the other glacial river. But these methylmercury concentrations were really low at less than 0.1 nanograms per liter. So we infer that the main source of mercury in this river system is the large glaciarized tributaries in this catchment. And by and large, we found that mercury was in the particulate phase from this large glaciarized river, and it associated with extraordinarily high concentrations of total suspended sediment of around 3,500 milligrams per liter. And this measurement was actually on the low side of typical late July concentrations of sediment in this river. Instead, the tributaries that drain glaciarized parts of the catchment, but then drain through these deep lakes, we inferred that these deep lakes act as very effective sediment traps, removing some of the mercury that could potentially travel downstream. And these deep lakes and also settling ponds that are used in the placer mining districts, these were potential methylation hotspots, but nevertheless, we found really low methylmercury concentrations in exports from these systems. So again, looking at this river system at large, we would suggest that the main source of mercury derives from these glaciarized components of the watershed that flow directly from the mountains. And that contributes to these relatively elevated mercury concentrations at the Yukon River at Dawson City, with all the other rivers relatively diluting mercury concentrations. And as these waters flow into Alaska, it's likely that other glacial rivers like the Tanana River contribute to higher mercury exports as well. These high mercury yields from a glacial catchment are not unique to us. Similar observations have been made in coastal Alaska by Andrew Verkhnyea and Sonia Nagorski. And of course, there's the contentious issue of whether mercury yields were also high from some glacial rivers in Greenland. But it does lead me to ask the question of whether it's possible that hard to access, remote, ungauged glacial rivers might still be an underestimated source of mercury to the Arctic Ocean. Rather than invoking high concentrations of mercury in sediments like was invoked in this study here in Alaska, we suggest that this glacial system that has surging type activity in its valley glaciers is simply scouring such enormous quantities of sediment on a daily basis that this is the main source of mercury downstream. For the Yukon River Basin itself, as glacier volume is lost, and it's being lost really rapidly, we would suggest that mercury exports from the Yukon River will decline in the future. And whether this is counterbalanced by increases from permafrost thaw is, in my opinion, yet to be determined, but I would argue it's not at present the main cause of high mercury exports at the outlet. So maybe you don't care about the Yukon River itself, but if I were to leave you with just one key takeaway message from my work, it's that geomorphology really matters. Thinking about the landscape history, the capacity for rivers to entrain sediment, the presence of deep water bodies or glacier dynamics in a catchment are all really important aspects to consider when we're thinking about how climate change or land use may impact mercury exports from Arctic rivers. So thank you so much for listening to my talk.